In the last section of Chapter 11, we're going to look at some general ideas about how to use chi-squared tests wisely. All right, an article in the Arizona Daily Star in 2009 included the following table. Suppose that you decide to analyze these data using a chi-squared test. However, without any additional information about how the data is collected, it is impossible to know which chi-squared test is appropriate. So let's look at this. First of all, let's explain why is it okay to use age as a categorical variable rather than a quantitative variable. Well, if you'll notice, the ages are grouped. It's not individual ages, they're grouped together. So because we're grouping them, they can be treated as categorical. Now the downside to this is that some information is lost, but it is a way to convert it to categorical data. Part B says, explain how you know that a goodness of fit test is not appropriate for analyzing these data. Well, remember, goodness of fit means you have one sample, one variable. If you look at this, it's a two-way table. You have two sets of variables going on here. So that is your big clue. It's not goodness of fit. So goodness of fit tests are only appropriate when you have one sample and one variable. This has two populations, the users of social network and non-users of social network. Or you could look at the age groups as populations. It just depends on how it was collected. So we know it's at least two, so it can't be goodness of fit. So part C says, describe how this data could have been collected so that a test of homogeneity is appropriate. So remember, test of homogeneity means I have two or more populations but one question. So we have some options, all right? First, we could have 6 independent random samples, one for each age group, and we could ask those people in each age group, are they social networkers or not? Okay, or we could have two groups, social networkers and non-social networkers. So, and we ask them, what's their age group? So there's two ways it could be homogeneity, two ways to look at it. So then D, how could the data have been collected so that a test for independence is appropriate? So independence, remember, is one population but two variables. Well, there's really only one way to do this. Well, you would take a simple random sample of people and ask them two questions, age group and social networking status. Now, which design did they use? We don't know, but this seems more reasonable, but we're not sure based on the question stem. They don't tell us. But this seems like the most reasonable. All right, so let's look at an example. In a study recorded by the Annals of Emergency Medicine in 2009, researchers conducted a randomized double-blind clinical trial to compare the effects of ibuprofen and acetaminophen, plus codeine as a pain reliever for children recovering from arm fractures. There were many response variables recorded, including the presence of adverse effects such as nausea, dizziness, drowsiness. But here's the result. A, which type of chi-squared test is appropriate here, and explain? Well, we have two groups of people. One group took ibuprofen, one group took acetaminophen plus codeine. It's like Tylenol plus codeine. So we have two separate groups, right? And then the question that we asked was, did you have adverse effects or not? So because I have two separate groups, that makes it a test of homogeneity. Two treatment groups, one variable. So B says calculate the chi-squared statistic and the p-value. So we're not going to run through the four-step process. We're just looking at the chi-squared and the p-value for right now. But to get chi-squared, I need my expected counts, right? So I did that. I did row total times column total divided by table total for each of these. And that's what you see in the orange. So when I calculate the chi-squared, I get a value of 11.15. And degrees of freedom, there's two columns minus 1, two rows minus 1. 1 times 1 is 1, so 1 degree of freedom. And then a p-value of 0.008. Okay, the calculator gave me all this to confirm. So with a p-value that's small, I would reject the null that there's no association between the treatment and the adverse effects. It means there must be some association there going on, right? And remember, our chi-squared value is 11.15. That'll come up here in a moment. Now part C says, show that the results of a two-sample Z test for a difference of proportions are equivalent to what we got in chi-squared. So if we look at this as proportions instead of categorical data, we can get a different, or get the same result actually. So if P1 is the proportion who had no side effects with ibuprofen. Okay, and P2 is the no adverse effects with the acetaminophen and codeine. And I do a 2-sample z-test with that. I get a z-value of 3.339. Okay, now if I square that, I get 11.15, which happens to be the exact thing as chi-squared. Why would I square it? Because it's a two-tailed test. Okay, and my p-value comes out to be 0.008. Same thing I had before. So notice if I do it as proportions versus categorical data, I end up with the same result. So then that brings up the next question. When should you use a chi-squared test and when should you use a 2-sample z-test? Great question. So let's look through this. Chi-squared is always and only going to be a 2-sided test. You can't measure less than or greater than with chi-squared. You can only do that with a 2-proportion z-test. So it depends on the problem stem in a lot of ways. If you want to estimate a difference, you have to use an interval. Chi-squared does not estimate a difference. Estimation only comes with confidence intervals. If you're comparing 2 treatments or 2 response variables, that means you can use the chi-squared. You're just comparing them. And then lastly, you can use chi-squared goodness of fit for testing whether P1 is not equal to P2. And it'll use success versus failure with a degree of freedom of 1. That's not that common, but you can do it. So it really depends on how the problem is set up and what they're asking you to find to determine which test it is. So look at this example. How could we compare the distribution of AP scores at Birdville versus Richland? Well, let's think through it. We could do a 2-sample t-test, but that would only compare the mean scores. The mean scores tell you only one little bit of information. It doesn't tell us the shape of the distribution, and that may be important, because if the shape of the distribution is right skewed or left skewed, that's some good information right there that the testing means won't tell us. But I have 2 samples and I have 1 variable, right? 2 high schools, 1 AP score that I'm looking at. That would mean I could use the test of homogeneity. Or I could do a 2-proportion z-test for the proportion of students who passed from each school. All right? All 3 are viable options. It just depends on what you're trying to get at when you're comparing them. Last question. What can you do if you run the expected counts and they're less than 5? Well, you can always combine rows and columns to make bigger categories or totals larger if you need to. You may lose some information in precision, but it is a viable option for you.